any war performs rather contradictory services for the social context in which it occurs. On the one hand, it changes the minds of men, especially the defeated, about the factual power relationship between the combatants. And, on the other hand, it alters the factual situation itself, so that changes which in peacetime might have occurred over decades are brought about in a few years. This has been true of all wars, but never has it been truer than in respect to World War II. The age which began in 1945 was a new age from almost every point of view. Looking back, it is now clear that the first generation of the 20th century, from about 1895 to 1939, was a long period of transition from the 19th century world to a totally different world of the 20th century. Some of these changes obvious: a shift from a period of democracy to an age of experts, from a world dominated by Europe, and even by Britain, to a world divided into three great blocks, from a world in which man still lived surrounded by nature, to a situation where nature is dominated, transformed and, in a sense, totally destroyed by man, from a system where man's greatest problems were the material ones of man's helplessness in the face of the natural threats of disease, starvation, and the unpredictability of natural catastrophes, to the totally different system of the 1960s and 1970s, where the greatest threat to man is man himself, and where his greatest problems are the social and non-material ones of what his true goals of existence are and what use he should make of his immense power over the universe, including his fellow men. For thousands of years, some men had viewed themselves as creatures a little lower than the angels, or even God, and a little higher than the beasts. Now, in the 20th century, man believes he has acquired almost divine powers, and it has become increasingly clear that he can no longer regard himself as an animal as the leading thinkers of the 19th century did, but must regard himself as at least a man if he cannot bring himself to break so completely with his 19th century predecessors as to come to regard himself as obligated to act like an angel or even a god. The whole trend of the 19th century had been to emphasize man's animal nature, and in doing so, to seek to increase his supply of material necessities, his indulgence in creature comforts, his experiences of food, movement, sex, and emotion. This effort had resulted in the sharp curtailment or almost total neglect of the conventions of man's earlier history, conventions which had been, on the whole, based on a conception of man as a dualistic creature in which an eternal spiritual soul was encased, temporarily, in an ephemeral, material body. This older conception had been embodied, in the form in which the 19th century challenged it, largely in the 17th century, and had been reflected in that earlier period in the widespread influence of Puritanism, of Jansenism, and of other, basically pessimistic, inhibiting, masochistic, and self-disciplining ideologies. The 18th century had been a long age of struggle to get free of this older, 17th century outlook, and had been so prolonged largely because those who turned away from the 17th century could neither envisage, nor agree upon, the newer ideology they wanted to put in the place of the older one they wished to reject. This newer ideology was found in the 19th century, and may be regarded as one which emphasized man's freedom to indulge his more animal-like aspects, to obtain freedom for his body from disease, death, hunger, discomfort, and drudgery. The outlook may be symbolized by Charles Darwin, whose writings came to stand for alleged proof of the animal nature of man, and of Sigmund Freud, whose writings were taken to allegedly show that sex was the dominant, if not the sole, human motivation, and that inhibitions were the great bane of human life. This latter point of view came to be accepted on the most pervasive level of human experience in the attacks on inhibitions and discipline which we call progressive education, as represented in the outpourings of such semi-popular thinkers as Rousseau in the earliest stage of the movement in Emile or John Dewey in the latest stage. Thus, the humanism of the 16th century had reacted against the scholasticism of the medieval period, and was reacted against in turn by the Puritanism of the 17th century, the materialism of the 19th century, and the reaction against this latest outlook by the flight from freedom and blind mass discipline of reactionary totalitarianism in the fascist and Nazi aberrations. This can be seen most essentially in the fact that the great achievements of the 19th century and the great crisis of the 20th century are both related to the Puritan tradition of the 17th century. The Puritan point of view regarded the body and the material world as sinful and dangerous, and, as such, something which must be sternly controlled by the individual's will. God's grace, it was felt, would give the individual the strength to curb both his body and his feelings, to control their tendencies toward laziness, the distractions of pleasure, and the diversions of enjoyment, and make it possible for the individual, by total application to work, to demonstrate that he was among the chosen recipients of God's grace. This Puritan outlook, rejected outwardly in the 19th century's vision of the truth, was, nevertheless, still an influential element in the 19th century's behavior, especially among those who contributed most to the 19th century's achievement of its own goals. The Puritan point of view contributed elements of self-discipline, self-denial, masochism, glorification of work, emphasis on the restrictions of enjoyment of consumption, and subordination both of the present to the future and of oneself to a larger whole. These became significant elements in the bourgeois, middle-class pattern of behavior which dominated the 19th century. The middle classes were themselves largely products of the 17th century, and had adopted this point of view as one of the features which distinguished them from the more self-indulgent attitudes of the other two social classes, the peasants below them or the aristocracy and nobility above them. In the 19th century, the elements of the Puritan point of view were quite detached from the otherworldly goals they had served in the 17th century, God and personal salvation, and were attached to individualistic and largely selfish, this worldly goals, but they carried over attitudes and patterns of behavior which remained largely detached from the 19th century's stated goals, and these, by a combination of 17th century methods with 19th century goals, produced the immense physical achievements of the 19th century. These methods appeared in a number of essential ways, notably in an emphasis on self-discipline for future benefits, on restricted consumption and on saving, which provided the capital accumulation of the 19th century's industrial development, in a devotion to work, and in a postponement of enjoyment to a future which never arrived. To such people, and to the prevalent middle-class ideology of the 19th century, the most adverse comments which could be made about a failure to distinguish him from a successful man were that he was a wastrel, a loafer, a sensualist, and self-indulgent. These terms reflected the value that the middle classes placed on work, saving, self-denial, and social conformity. All these values were carried over from 17th century Puritanism, and were found most frequently among the religious groups rooted in that century: the Quakers, Presbyterians, Nonconformists so-called in England, and Jansenist survivals, and were less evident among religious groups with older orientations, such as Roman Catholics, High Anglicans, or Orthodox Christians. These older creeds were more prevalent among the lower and the upper classes and in Southern and Eastern Europe rather than in Northern or Western Europe. This explains why the energy, self-discipline, and saving which made the world of 1900 was middle class, Protestant, and Northwestern European. As we shall see later, in discussion of the American crisis of the 20th century, these outlooks, values, and groups are now being superseded by quite different outlooks, values, and groups. We shall speak later of these essential features of the 19th century point of view, because their disappearance in the 20th century, associated as it is with the crisis of the middle classes, is an essential part of the crisis of the 20th century, where it is to be seen most clearly in the English-speaking and Scandinavian countries. We shall call these features, as a single bundle, future preference, and understand that it includes the gospel of saving, of work, and of postponed enjoyment, consumption, and leisure. Closely related to it is a somewhat different idea, based on a constant and irremediable dissatisfaction with one's present position and present possessions. This is associated with the 19th century's emphasis on acquisitive behavior, on achievement, and on infinitely expansible demand, and is equally associated with the middle-class outlook. Both of these together, future preference and expansible material demands, were basic features in 19th century middle-class society, and indispensable foundations for its great material achievements. They are inevitably lacking in backward, tribal, underdeveloped peasant societies and groups, not only in Africa and Asia but also in many peripheral areas and groups of Western civilization, including much of the Mediterranean, Latin America, Central France, or in the Mennonite communities of southern Pennsylvania and elsewhere. The lack of future preference and expansible material demands in other areas, and the weakening of them in middle-class Western civilization, are essential features of the 20th century crisis. Though this crisis, which has appeared as a breakdown, disruption, and rejection of the 19th century's way of doing things, was fully evident by the year 1900, it was brought to an acute stage by the two world wars and the World Depression. If we may be permitted to oversimplify, two antithetical ways of dealing with this crisis appeared. One way, going back to men like George Sorel's Reflections on Violence, 1908, sought a solution of this crisis in irrationalism, in action for its own sake, in submergence of the individual into the mass of his tribe, community, or nation, in simple, intense concrete feelings and acts. The other tendency, based on 19th century science, sought a solution of the crisis in rationalization, science, universality, cosmopolitanism, and the continued pursuit of eternal, if rapidly retreating, truth. While the great mass of people in Western civilization either ignored the problem and the antithetical character of the two proffered solutions, drifting unconsciously toward the one or struggling confusedly toward the other, two smaller groups were quite aware of the antithesis and rivalry of the two. From the crisis itself and the myriad individual events which led through it, came World War II. Although few were consciously aware of it, this war became a struggle between the forces of irrationality, represented by fascism, and the forces of Western science and rationalization, represented by the Allied nations. The Allied nations won this fearful struggle because they represented the forces of the ancient traditions of the West which had made Western civilization the most powerful and most prosperous civilization that had ever existed in the past 6,000 years of experience of this form of human organization. This ability to use the Western tradition appeared in a capacity to use rationalization, science, diversity, freedom, and voluntary cooperation, all long-existent attributes of Western civilization. The application of rationalization and science to World War II is one of the basic reasons, although not necessarily the most important reason, for the victory of the West in the war. As a consequence of that victory, these two methods survived the challenge from reactionary, totalitarian, authoritarian fascism, and expanded from the limited areas of human experience where they had previously operated to become dominant factors in the 20th century world. The two obviously not identical, and neither is equivalent to rationalism, although both use rationalism as a prominent element in their operations. Rationalism, strictly speaking, is a rather unconvincing ideology. It assumes that reality is rational and logical, and, accordingly, is comprehensible to man's conscious mental processes, and can be grasped by human reason and logic alone. It assumes that what is rational and logical is real, that what is not rational and logical is dubious, unknowable, and unimportant, and that the observations of the human senses are unreliable or even illusory. Rationalization and science differ from rationalism in two chief ways. One, they are more empirical, in that they are willing to use sense observations, and two, they are more practical, in that they are more concerned with getting things done in the temporal world than they are with discovering the nature of ultimate truth. They do not necessarily deny the existence of such an ultimate truth, but they agree that any conclusions reached about its nature, using their methods, are proximate rather than ultimate. Both methods, thus, are analytical, tentative, proximate, modest, and relatively practical. The chief difference between them is that science is a somewhat narrower subdivision of rationalization, because it has a more rigid and self-conscious methodology. Taken together, these two have played significant roles in Western civilization for centuries, but have always remained somewhat peripheral to the experience of ordinary men. One of the chief consequences of World War II is that they are no longer peripheral. Of course, it must be recognized that rationalization and science are not yet, by any means, central to the experience of ordinary men, or even to the majority of men. But now they almost certainly must become matters of first-hand experience for the majority of men if Western civilization is to survive. As the novelist of these matters, Sir Charles P. Snow, has said, scientists increasingly play a vital role in those crucial, secret decisions which determine in the crudest sense whether we live or die. Before World War II, science was recognized by all to be a significant element in life, but few had first-hand contact with it, and very few had any real appreciation of its nature and achievements. It was reserved largely for academic people, and for a small minority of these, and it touched the lives of most men only indirectly, by its influence on technology, especially on medical practice, transportation, and communications. There was very clearly, before 1939, what Sir Charles Snow has called two societies in our one civilization. This meant that most men lived in an ignorance of science almost as great as that of the Hottentot and almost equally great among highly educated professors of literature at Harvard, Oxford, and Princeton. It also meant that scientists were quite out of touch with the major realities of the world in which they lived, and were smitten by the impacts of war, depression, and political disturbances under conditions of ignorance, naivete, and general bafflement at least as great as that of the uneducated, ordinary man. World War II brought science into government, and especially into war, and brought politics, economics, and social responsibility into science in a way which must be beneficial to both but which was almost unimaginably shocking to both. Reading, for example, the interchange of questions and answers which go on between scientists and politicians before congressional committees concerned with outer space, Atomic energy for medical research is a revelation of the almost total lack of communication which takes place behind that prolific interchange of words. The impact of rationalization is almost as great, although much less recognized. It had always existed in an incidental and minor way in men's experiences, but hardly justified a special name until it became a conscious and deliberate technique. It is a method of dealing with problems and processes in an established sequence of steps. Thus, 1. Isolate the problem. 2. Separate it into its most obvious stages or areas. 3. Enumerate the factors which determine the outcome desired in each stage or area. 4. Vary the factors in a conscious, systematic, and if possible quantitative way to maximize the outcome desired in the stage or area concerned. And 5. Reassemble the stages or areas and check to see if the whole problem or process has been acceptably improved in the direction desired. Such rationalization is analytical and quantitative, even numerical. It was first used on an extensive scale at the end of the 19th century to solve problems of mass production, and led, step by step, to assembly line techniques in which regulated quantities of materials, parts, power, labor, and supervision were delivered in a rational arrangement of space and time, to produce a continuous outflow of some final product. All elements in the process were applied to measurable units to a system operated in accord with a dominant plan to achieve the desired result. Naturally, such a process serves to dehumanize the productive process, and, since it also seeks to reduce every element in the process to a repetitive action, it leads eventually to an automation in which even supervision is electronic and mechanical. From the basically engineering problem of production, rationalization gradually spread into the more dominant problem of business. From maximizing production, it shifted to maximizing profits. This gave rise to efficiency experts such as Frederick Winslow Taylor, whose The Principles of Scientific Management appeared in 1911, and, eventually, to management consultants, like Arthur D. Little, Incorporated. This point had been reached by 1939, when rationalization was still remote from ordinary life and very remote from politics and war. As in so many other innovations, the introduction of rationalization into war was begun by the British and then taken over, on an enormous scale, by the Americans. Its origin is usually attributed to the efforts of Professor P.M.S. Blackett Nobel Prize, 1948, to apply radar to anti-aircraft guns. From there Blackett took the technique into anti-submarine defense, whence it spread, under the name Operational Research Opus, into many aspects of the war effort. In its original form, the Anti-Aircraft Command Research Group, known as Black's Circus, included 3 physiologists, 2 mathematical physicists, 1 astrophysicist, the surveyor, the general physicist, 2 mathematicians, and an army officer. It was a mixed team approach to operational problems, emphasizing an objective, analytical, and quantitative method. As Blackett wrote in 1941, the scientist can encourage numerical thinking on operational matters, and so can help to avoid running the war on gusts of emotion. Operational research, unlike science, made its greatest contribution in regard to the use of existing equipment rather than to the effort to invent new equipment. It often gave specific recommendations, preached through the techniques of mathematical probability, which directly contradicted the established military procedures. A simple case concerned the problem of their attack on enemy submarines. For what depth should the bomb fuse be set? In 1940, the RAF Coastal Command set its fuses at 100 feet. This was based on estimates of three factors. 1. The time interval between the moments the submarine sighted the plane and the plane sighted the submarine. 2. The speed of approach of the plane. And 3. The speed of submergence of the submarine. One fixed factor was that the submarine was unlikely to be sunk if the bomb exploded more than 20 feet away. Operational research added an additional factor. How near was the bomber to judging the exact spot where the submarine went down? Since this error increased rapidly with the distance of the original sighting, the submarine which had time to submerge deeply would almost inevitably be missed by the bomb in position if not in depth. But, with 100-foot fuses, submarines which had little time to submerge were missed because the fuse was too deep even when the position was correct. Opus recommended setting fuses at 25 feet to sink the near sightings, and practically conceded the escape of all the distant sightings. When fuses were set at 35 feet, successful attacks on submarines increased 400% with the same equipment. The British applied Opus to many similar problems, one with an inadequate number of AA guns. Is it better to concentrate them to protect part of a city thoroughly or to disperse them to protect all of the city inadequately? The former is better. 2. Repainting night bombers from black to white when used on submarine patrol increased sightings of submarines 30%. 3. Are small convoys safer for merchant ships than large ones? No, by a large margin. For with an inadequate number of patrol planes, was it better to search the whole patrol area some days as was the practice, or to search part of it every day with whatever planes were available? Calculations of a mathematician, S.D. Poisson, who died in 1840, showed that the latter was better. Some of Opp's improvements were very simple. For example, a statistical study of sightings of German submarines by patrol planes showed that twice as many were seen on the left side of the plane as on the right side. Investigation showed this was because the plane flew on automatic pilot, allowing the pilot on the left side almost full time to watch the sea, while the co-pilot on the right side was busy much of the time. Assignment of another crewman to the right side when the co-pilot was busy increased sightings about 30%. Until late 1941 the RAF bombed German cities as they were able. Then Opus, using the German bombing of Britain as a base, calculated the number of people killed per ton of bombs dropped, and applied this to Germany to show that the casualties inflicted on Germany were about 400 civilians killed per month, about half the German automobile accident death rate. While 200 RAF crewmen were killed per month in doing the bombing. Such bombing could never influence the outcome of the war. Later it was discovered that the raids were really killing only 200 German civilians, almost all non-combatants, contributing little to the war effort at the cost of the 200 RAF fighting men each month, and thus were a contribution to a German victory. These estimates made it advisable to shift planes from bombing Germany to U-boat patrol, so that the German submarine war, which was really strangling Britain, could be brought under control. A bomber, in its average life of 30 missions, dropped 2 tons of bombs on Germany, killing 20 Germans and destroying a few houses. The same plane in 30 missions of submarine patrol saved, on the average, 6 loaded merchant vessels and their crews from submarines. As might be expected, this discovery was violently resisted by the head of the RAF Bomber Command, Chief Marshal Sir Arthur Bomber Harris. Closely linked with this was the question whether it was better to use Britain's shipbuilding capacity to construct escort vessels or merchant ships. This involved the choice between saving existing merchant ships or outbuilding the losses from submarines. It required a statistical study of the effectiveness of escort vessels. At the time, the Admiralty regarded small convoys as safer and large ones as dangerous, and had forbidden convoys of over 60 ships. They assigned escort vessels to each convoy at the rate of 3 plus 1/10 of the number of ships protected. Opus W is able to show that this assignment rule was inconsistent with the prejudice against large convoys. Studying past losses, they showed that convoys of under 50 ships averaging 32 each suffered losses of 2.5%. While large convoys of over 40 ships averaging 54 ships each were twice as safe, with losses of only 1%. Using information from rescued German U-boat crews, Opus was able to show that U-boat success depended on the density of escort vessels around the perimeter of the convoy, and that the percentage of ships sunk was inversely proportional to the size of the convoy. By 1944 a convoy of 187 ships arrived without loss. If the shift to large convoys had been made in the spring of 1942, rather than in the spring of 1943, 1,000,000 tons of merchant shipping or 200 ships could have been saved. The combination of larger convoys, and the shift of some planes from bombing Germany to submarine patrol, turned the corner on the U-boat menace in the summer of 1943 and helped save many ships which were used in the Allied amphibious landings, especially on D-Day in 1944. The shock of the fall of France in June 1940 marked a turning point in the relations between universities and government in the United States. At that time, the chief contacts between the two were the National Academy of Sciences, founded in 1863, and the National Advisory Committee for Aeronautics (NACA), founded in 1915. The former DV is a non-governmental body electing its own members from American scientists and bound to advise the government, upon request, in scientific or technical matters. The dependent body, the National Research Council, had members from the government at large and representatives of over 100 scientific societies to act as liaison between the Academy and the scientific community. The NACA was a government agency which performed a similar function in aeronautics and did extensive research in its field with government funds. In 1938 Vannevar Bush, Professor of Electrical Engineering and Vice President of Massachusetts Institute of Technology, an outstanding figure in applied mathematics and electronics, best known as the inventor of the differential analyzer for mechanical solution of differential equations in calculus, became a member of NACA. The following year he became president of the Carnegie Institution of Washington and chairman of NACA. As France fell, Bush persuaded President Roosevelt to create the National Defense Research Committee with Bush as chairman. The 12 members served without pay, and consisted of 2 each from the Army, the Navy, and the National Academy of Sciences, with 6 others. Bush named Frank B. Jewett, president of Bell Telephone Laboratories and the NAS, Carl T. Compton, president of MIT, James B. Conant, president of Harvard, Richard C. Tolman, of California Institute of Technology, and others. They set up headquarters at the Carnegie Institution and Dumbarton Oaks, a Harvard Byzantine Research Center in Washington. The NDRC in its first year gave over 200 contracts to various universities, and thus established the pattern of relations between government and the universities which still exists. In the first year it spent only $6.5 million, but in the 6th year 1940-1946 it spent almost $454 million. During that whole period, there was only one shift in the civilian personnel of the NDRC. In May 1941 the higher and wider organization was created, the Office of Scientific Research and Development OSRD, with Bush as chairman and Conant as his deputy. Conant took Bush's place as chairman of NDRC, and Roger Adams, professor of chemistry at the University of Illinois, was added to NDRC. These groups were the supreme influence in America in introducing rationalization and science into government and war in 1940-1946, fostering hundreds of new technical developments and inventions, including the atom bomb. One of their earliest acts was to make the census of research facilities and a national roster of scientific and specialized personnel with 690,000 names. They did not hesitate to call upon the services of both as needed. When money ran short, they found it from private sources, as in June 1941, when, simply by asking, they obtained $500,000 from MIT and an equal sum from John D. Rockefeller, Jr., to pay salaries when congressional appropriations ran short. Somewhat similar organizations grew up in Britain, in the Soviet Union, and in the enemy countries, but none worked so successfully as that of the Americans, who, here, as elsewhere, showed a genius for improvised large-scale organization. On the whole, the British were more fertile in new ideas than the Americans, probably because they were less conventional in their thinking processes, but the Americans were superior in development and production. The Soviet Union, which was very lacking in new ideas, was fairly successful considering its obvious handicaps, such as enemy invasion and industrial backwardness in development. Its organization was somewhat like that in the United States, but much more centralized, since its Academy of Sciences controlled government funds and allotted both tasks and funds to university and special research groups. Germany, which had a high degree of innovation comparable to that in the United States, was paralyzed by myriad conflicting and overlapping authorities in control of development and production, and by the fact that the whole chaotic mess was under the tyranny of vacillating autocrats. Japan, almost lacking in innovation, achieved a surprising degree of production under a system of conflicting autocratic authorities almost as bad as that of Germany. Rationalization of behavior, as represented in operations research, and the application of science to new weapons, as practiced by the English-speaking countries, were in sharp contrast with the methods of waging war used by the tripartite aggressors. Hitler fought the war by basing his hopes on inspiration, his own and willpower usually. Refusal to retreat an inch. Mussolini tried to fight his war on rhetoric and slogans. The Japanese tried to gain victory by self-sacrifice and willingness to die. All three irrational methods were obsolete as compared with the Anglo-American method of rationalization and science. First news of the success of operations research in Britain was brought to the United States by President Conant in 1940 and was formally introduced by Vannevar Bush, as chairman of the New Weapons Committee of the Joint Chiefs of Staff, in 1942. By the end of the war, the technique had spread extensively through the American war effort, and, with the arrival of peace, became an established civilian profession. The best-known example of this is the Rand Corporation, a private research and development firm, under contract to the United States Air Force. But numerous lesser organizations and enterprises are now concerned with rationalization techniques in political life, the study of war and strategy, in economic analysis, and elsewhere. Similar groups arose in Britain. One of the most complex applications of the technique has been Operation Bootstrap, by which the Puerto Rican Industrial Development Corporation, advised by Arthur de Little, Incorporated, has sought to transform the Puerto Rican economy. Persons interested in opus have organized societies in England 1948 and the United States 1949, which publish a quarterly and a journal. A great impetus has been given to the rationalization of society in the post-war world by the application of mathematical methods to society to an unprecedented degree. Much of this used the tremendous advances in mathematics of the 19th century, but a good deal came from new developments. Among these have been applications of game theory, information theory, symbolic logic, cybernetics, and electronic computing. The newest of these was probably game theory, worked out by a Hungarian refugee mathematician, John von Neumann, at the Institute for Advanced Study. This applied mathematical techniques to situations in which persons sought conflicting goals in a nexus of relationships governed by rules. Closely related to this were new mathematical methods for dealing with decision-making. The basic work in the new field was the book Theory of Games and Economic Behavior, by John von Neumann and Oscar Morgenstern, Princeton, 1944. Similar impetus to this whole development was provided by two other fields of mathematics in which the significant books in America were C. E. Shannon and W. Weaver. The Mathematical Theory of Communication, University of Illinois, 1949, and Norbert Wiener, Cybernetics, or Control and Communication in the Animal and the Machine, Massachusetts Institute of Technology, 1949. A flood of books have amplified and modified these basic works, all seeking to apply mathematical methods to information, communications, and control systems. Closely related to this have been increased use of symbolic logic, as in Willard von Orman Quine, Mathematical Logic, Harvard, 1951, and the application of all these to electronic computers, involving large-scale storage of information with speedy retrieval of it and fantastically rapid operations of complex calculations. These, and related techniques, are now transforming methods of operation and behavior in all aspects of life and bringing on a large-scale rationalization of human life, which is becoming one of the most significant characteristics of Western civilization in the 20th century. Closely related to all this, both in the war and in the post-war period, have been advances in science. Here, also, the great impetus came from the struggle for victory in the war and the subsequent permeation of all aspects of life by attitudes and methods, in this case science, which had been peripheral to the experience of most people in the pre-war period. The consequences of this revolution now surround us on all sides and are obvious, even to the most uncomprehending, in television and electronics, in biology and medical science, in space exploration, in automation of credit, billing, payroll, and personnel practices, in atomic energy, and above all in the constant threat of nuclear incineration which now faces all of us. In much of this the fundamental innovations were British, or at least European, but their full exploitation and production processes have been American. The mobilization of these processes under the OSRD and NDRC by those two Massachusetts Yankees, Bush and Conant, is one of the miracles of the war. In sharp contrast with the OSS, it achieved its goals with a minimum of administrative friction, by the use of existing agencies, except in the few cases, such as the atom bomb, where no agency had existed previously. Probably no new group in the history of American government achieved so much with such a high degree of helpful cooperation. Most of this was the result of Bush's broad vision, tact, and total lack of desire for personal celebrity. Much of it was done quietly in individual discussions and unpublicized committee meetings. For example, as chairman of the Joint Committee on New Weapons and Equipment (JNW) of the Joint Chiefs of Staff from its founding in May 1942 to the end of the war, Bush achieved wonders, not only in persuading military men to use new weapons and new techniques but also in persuading the different services to integrate their introduction of new methods and their future plans. The impetus to the use of science in many fields came from the British. This began in World War I when men like Sir Henry T. Dysart, Sir Robert A. Watson Watt, and Professor Frederick A. Lindemann Lord Charles after 1956 studied aviation problems scientifically. This link between government and science in aviation was maintained in Britain, as in the United States, during the Long Armistice. After Hitler came to power, Dr. H. E. Whymper Rice, Director of Scientific Research at the Air Ministry, and his colleague A. P. Rote, set up a committee on research on air defense, with Dysart as chairman and Rote as secretary, with Professors A. B. Hill and P. M. S. Blackett as members, and Watson Watt as consultant. Professor Hill, physiologist, had won the Nobel Prize in 192, while Blackett, ex-naval officer and nuclear physicist, was the initiator of operational research and won the Nobel Prize in Physics in 1948. Watson Watt may be regarded as the chief discoverer of radar. In sharp contrast with OSRD and NDRC in America, this committee had a stormy life. In 1908, while studying physics in Berlin with Walter Nernst Nobel Prize, 1920 Dysart met a fellow student, F. A. Lindemann, who was born and educated as a German, but held the British passport from his wealthy father's naturalization in England before his birth. Lindemann became a moody, driving, uncompromising, and erratically trained amateur scientist who devoted his best hours and energy to upper-class English social life, and combined intermittent flashes of scientific brilliance with total lack of objectivity and consistently poor judgment. Dysart, a fairly typical English civil servant, was, nonetheless, attracted to Lindemann, and in 1919 helped secure for him an appointment as Professor of Experimental Philosophy at Oxford. At the time, science was at a low ebb at Oxford, and Lindemann, over the next 2 decades, built up its Clarendon laboratory toward the high level which the Cavendish laboratory at Cambridge University had achieved under Lord Rutherford. During this period Lindemann became the close friend and scientific advisor of Winston Churchill. Through Churchill's influence, Lindemann was forced on Dysart's Committee for the Scientific Survey of Air Defense, where he acted as a disruptive influence from July 1935, until the 3 scientific members Hill, Blackett, and Whymper forced him off in September 1936 by resigning together. The whole committee was then dissolved and reappointed under Dysart without Lindemann. The latter reversed the tables for years later when Churchill became Prime Minister with Lindemann as almost his only scientific advisor. teaser was dropped from the committee in June 1940. But by that time the great work in radar was done. The Tizard Committee, with only £10,000 for research, held its first meeting on January 28, 1935, and by June 16, before Lindemann joined, had a radar set on which they followed a plane 40 miles. On March 3, 1936, they identified the plane flying at 1,500 feet 75 miles away. In September 1938, 5 stations southeast of London followed Chamberlain's plane flying to the Munich conference, and on Good Friday 1939, as Mussolini was invading Albania, the chain of 20 stations began continuous operations along the eastern coast. One of the chief advances here was Watt's use of a cathode vacuum tube such as we now use in television to watch the returning radio signal. This signal, sent out from a radio vacuum tube in pulses, returned through the crystal detector to appear as a blip, or spot, on the cathode tube's fluorescent screen. The shorter the wavelength of the sending wave, the sharper and more accurate the returning signal, the shorter the necessary aerial, and the lower the transmitting hour. But vacuum tubes could not broadcast waves less than low meters in length, 300,000 kilocycles. Just as the war began, Professor John T. Randall, at the University of Birmingham, invented the resonant cavity magnetron, an object no bigger than a fist, which broadcasts high-powered, very short, radio waves. This ended interference from ground reflections or reflections from the ionosphere, and allowed sharp discrimination of objects without need for long antennae or height hours. By the time the magnetron came into use 1941, broadcasting from tubes had been improved to allow use of 1.5-meter waves, but the magnetron was developed for 0.1-meter waves. All subsequent radar development was based on it. At the same time, great advances were being made in crystals for detectors. This later grew into the use of artificial crystal transistors for amplification in receivers as well as for detection. In August 1940, Sir Henry Tizard, ousted from his committee by Lindemann, led the British scientific mission to Washington. He brought a large box of blueprints and reports on British scientific work, including radar, the new explosive RDX, half again as powerful as TNT, studies on gaseous diffusion of uranium isotopes for an atom bomb, and much else. This visit gave a great impetus to American scientific work. As one consequence of it, 350 men from the United States were working in the radar net stations in England by November 1941, a month before Pearl Harbor. Of the many inventions which emerged from science in World War II, we have space here to mention only a few: shaped charges, proximity fuses, medical advances, and the atom bomb. 600 years of ordnance research on artillery had brought guns to a high state of excellence long before World War I, but artillery, with all its advantages of range and accuracy, had three intrinsic disadvantages. The backward thrust of the explosive gases of propulsion gave it a violent recoil. The same gases corroded and wore down the inside of the barrel very rapidly, and the projectile, on hitting the target, dispersed its explosive force, sending most of it backward into the air from the resistance of the target itself. The rocket avoids the first two of these problems because it directs the recoil forward to push the rocket, and needs no container barrel at all. The Russians, who had greatly developed the use of rockets, used them in large numbers against the Germans in 1941. Since rockets need no barrel to shoot through but merely require a holder until they can fully ignite, rockets allowed an infantryman to supply his own artillery support, especially against tanks. By the end of the war, American rockets were delivered for use in individual, disposable plastic launchers which were thrown away after the rocket inside had been fired. The great disadvantages of rockets were their inaccuracy and short range, both of which came from the weak and uneven burning of the propellant. Great improvements were made in the study of propellants by the Germans, especially from the work of Hermann Oberth, Walter Dornberger, and Werner von Braun at Piedmont Rocket Research Institute on the Baltic Sea. These men, working on the basis of earlier studies by the American professor Robert H. Goddard, a method of reaching extreme altitudes, 1929, and by a Polish high school teacher in Russia, K. Ziolkowski, 1857, 1935, greatly advanced rocketry during the war and developed the V-2, which devastated London and Antwerp from September 8, 1944 until the war's end. The English had been expecting this attack, since a German test rocket had gone astray in June 1944, and had exploded over Sweden. The pieces from it, which were handed over to the Allies, made it possible to reconstruct the characteristics of the rocket, but left them in dread that it was being held back until the Germans could perfect an atomic bomb warhead. From this point of view, the first V-2 on England at 6:43 p.m. September 8, 1944, followed by another 16 seconds later, was a relief. They carried warheads of conventional explosives, but that warhead of 1,654 pounds came in on a 46-foot rocket traveling at 3 times the speed of sound, coming down from an altitude of 60 miles from a launching site 200 miles away. More than 1,100 of these rockets killed 3,000 British before they were stopped. Just as a rocket reverts the recoil of a gun, directing it forward, so a shaped charge reverts the shape of the projectile. An artillery projectile is bullet-shaped, with its forward end pointed or convex. In 1888, C. Monroe had shown that if the explosive charge were made concave, with the cavity at its forward end against the target, the explosive force would be directed forward toward the target as rays of light go forward from a concave headlight cavity instead of backward. The American bazooka of 1942 combined this shaped charge with a rocket to provide an infantry weapon with which a single man could knock out a tank. a relatively small charge carried to a tank with an impetus no greater than a well-hit baseball exploded most of its power forward in a narrow pencil of explosive force which sometimes penetrated 6 inches of armor or 6 feet of masonry. A hole less than an inch wide on the tank could destroy its crew by spraying them with molten metal forced inward from the shaped charge. In a few cases, this occurred through 8-inch armor without the armor being fully penetrated. Thus the tank, triumphant in 1940, was brought under control, and by 1945 was used largely as mobile artillery. An even more remarkable advance was the proximity fuse. This was a fuse containing a tiny radar set which measured the distance to the target and could be adjusted to explode at a fixed distance. First used to explode AA shells within lethal distance of enemy planes, it soon was adapted to explode just over the heads of ground forces. The latter use, however, was not permitted for more than 2 years, for fear the enemy would obtain the dub and be able to copy it. The proximity VD fuse was, after the atom bomb, the second greatest scientific achievement of the war, although the magnetron contributed more than either to an Allied victory. Producing the fuse seemed impossible. It would be necessary to make the radar sending and receiving set to fit in a space smaller than an ice cream cone, to make it strong enough to withstand 20,000 times the force of gravity in original acceleration and the spin in flight of 475 rotations per minute, to have it detonate at a precise instant in time with no chance of exploding earlier to endanger the gunner, and to be sure that it would explode entirely if it missed its target zone so that there would never be a dud. These problems were solved, and production began in 1942. By the end of the war, Sylvania had made over 130 million minute radio tubes, of which 5 were needed in each fuse. First used in action by the USS Helena against a Japanese dive-bombing plane on January 5, 1943, it destroyed the attacker on the second salvo. In order of the combined chiefs of staff prohibited use of the fuse except over water, where the enemy could not recover duds. But late in 1943 secret intelligence obtained plans of the VL robot plane which Hitler was preparing to bomb London. The CCS released proximity fuses to be used over England against this new threat. The first VL came over on June 12, 1944, the last, 80 days later, the VD fuses being used only during the final 4 weeks. In the last week, VD fuses destroyed 79% of the VLs that came over. On the final day only 4 out of our over reached London. They were being destroyed by 3 machines developed by NDRC and made in the United States, detected by SCR 580 for radar, their courses predicated by M9 computers, and shot down by VD fuses. General Sir F.A. Pyle, Chief of British AA Command, sent Bush a copy of his report on this operation, inscribed, "With my compliments to OSRD who made the victory possible." The VV fuse was released by CCS for general use on land at the end of October 1944, and was first used against German ground forces in the Battle of the Bulge. The results were devastating. In thick fog the Germans massed their men together, believing they were safe since the range could not be measured for orthodox artillery time fuses. They were massacred by VV shells exploding over their heads, and even those who crouched in foxholes were hit. On another evening, near Bastogne, German tanks were observed entering the wood for the night. After they were settled, the area was blasted with VV shells. In the morning 17 German tanks surrounded by their dead crews were found in the area. One of the greatest victories of science in the war was in the treatment of the wounded. 97% of the casualties who reached the front line dressing stations were saved, a success which had never been approached in earlier wars. The techniques which made this possible, involving blood transfusions, surgical techniques, and antibiotics, have all been continued and amplified in the post-war world. Although the destruction of man's natural environment by advancing technology has created new hazards and new causes of death by advancing cancer, disintegrating circulatory systems, and increasing mental breakdowns, the greatest achievement of science during the war, and, indeed, in all human history, was the atom bomb. Its contribution to victory was secondary, since it had nothing to do with the victory over Germany and at most shortened the war with the Japanese only by weeks. But this greatest example of the power of cooperating human minds has changed the whole environment in which men live. The only human discovery which can compare with it was man's invention of the techniques of farming almost 9,000 years earlier. But this earlier advance was slow and empirical. The advance to the atom bomb was swift and theoretical, in which men, by mathematical calculations, were able to anticipate, measure, judge, and control events which had never happened previously in human experience. It is not possible to understand the history of the 20th century without some comprehension of how this almost unbelievable goal was achieved, and especially why the Western powers were able to achieve it, and the fascist powers were not. As late as the fall of France in 1940, all countries were equal in their scientific knowledge, because science was then freely communicable, as it must be, by its very nature. Much of that knowledge, in physical science, rested on the theories of three Nobel Prize winners of 1918 to 1922. These were Max Planck (1858 to 1947), who said that energy did not move in a continuous flow like water but in discrete units, called quanta, like bullets. Albert Einstein (1879 to 1955), whose theory of relativity indicated that matter and energy were interchangeable according to the formula E equals mc2, and Niels Bohr (1885, 1962), who offered the picture of the atom as a planetary structure with a heavy, complex nucleus, and circumrotating electrons in fixed orbits established by their energy levels according to Planck's quantum theory. At that time, 1940, all scientists knew that some of the heavier elements naturally disintegrated and were reduced to somewhat lighter elements by radioactive emission of negatively charged electrons or of positively charged alpha particles, helium nuclei, consisting of two positively charged protons with two uncharged neutrons. As early as 1934, in Rome, Enrico Fermi Nobel Prize, 1938, and Emilio Segre Nobel Prize, 1959, without realizing what they had done, had split uranium atoms into lighter elements, chiefly barium and krypton, by shooting neutrons into the uranium nucleus. Such neutrons had been isolated and identified in 1932 by Sir James Chadwick, Nobel Prize winner in 1935. Although Ida Noddack at once suggested that Fermi had split the atom, the suggestion was generally ignored until Otto Hahn, Lisa Meitner, and Fritz Strassmann in Germany, in 19,371,939, repeated Fermi's experiments and sought to identify the bewildering assortment of lighter radioactive elements which emerged when uranium was bombarded with a stream of neutrons. By February 1939, it was established that the heaviest element, 92 uranium, could be split in various ways into lighter elements nearer the middle of the atomic table, and that large amounts of energy were released in the process. For example, 92 uranium might be split into 56 barium and 36 krypton. The reason for the release of energy was that the nuclear particles, protons and neutrons, had smaller masses in the nucleus of elements near the middle of the atomic table than they had in the nuclei of elements nearer the top or the bottom of the table, or than the particles had alone outside any nucleus. This meant that the nuclear particles had the least mass in the elements near 26 iron, and that energy would be released if heavier elements could be broken into lighter ones nearer iron, or if lighter elements could be built up into heavier elements nearer iron. Now that scientists can do both of these things, at least at the very top hydrogen and the very bottom uranium of the table, we call the splitting process fission and the building up process fusion of nuclei. As explosive forces, they are now represented by the atomic bomb and the hydrogen thermonuclear bomb. The amount of energy released by either process can be calculated by Einstein's equation, E equals mc2, where c is the speed of light, 30 billion centimeters, or about 186,000 miles a second. By this equation, if only an ounce of matter is destroyed, 5,600,000 kilowatt-hours of energy would be released. In 1939, of course, no one could conceive how lighter elements could be fused into heavier ones. As scientists had just revealed, uranium could be fissured. To the historian of these events, the months of January and February are of crucial significance. On January and Fermi, self-exiled from Mussolini's Italy, reached New York with his wife and children, from Stockholm, where he had just received the Nobel Prize. 4 days later, the Hans Strassmann report on uranium fission was published in Germany, and Otto Frisch, sent by his aunt, Lisa Meitner, from Sweden, where they were both refugees from Hitler's Germany, dashed to Copenhagen to confer with Bohr on the real meaning of Hans' report. Bohr left the next day, January 7, to join Einstein at the Institute for Advanced Study in Princeton, while Frisch and Meitner, in Sweden, repeated Hans' fissure of uranium and reported on the results in quantitative terms, in the English journal Nature on February 1 and 18, 1939. These reports, which first used the word fission, introduced the atomic age, and showed that, wait for weight, uranium fission would be 20 million times more explosive than TNT. Such a burst of energy would, of course, not be noticed in nature if only a few atoms of uranium split. Moreover, no large number would split unless the uranium was so pure that its atoms were massed together, and unless the stream of splitting neutrons continued to hit their nuclei. Immediately, in February 1939, the number of scientists thought that these two conditions, which do not exist in nature, might be created in the laboratory. It took only a few minutes to realize that this process would become an almost instantaneous chain reaction if extra neutrons, to serve as fission bullets, were issued by the splitting process. Since the uranium nucleus has 146 neutrons, while barium and krypton together have only 82 plus 47, or 129, it is obvious that each split uranium atom must release 17 neutrons capable of splitting other uranium atoms if they hit their nuclei with the right momentum. This idea was tested at once by Frédéric Joliot-Curie Nobel Prize, 1935 in Paris, and by Fermi and another refugee, Émile Szilard, with their associates, at Columbia University, New York. The three teams submitted their reports to publication in March 939. Bohr and others had already suggested that large-scale uranium fission does not occur in nature because natural uranium was widely dispersed atomically by being overwhelmingly diluted in chemical combination and mixture with other substances in its ores. They pointed out also that even pure natural uranium would probably not explode, because it was a mixture of three different kinds, more isotopes, of uranium, all with the same atomic number 92 and thus with the same chemical reactions, since these are based on the electrical charge of the nucleus as a whole but with quite different atomic weights of 234, 235, and 238. These isotopes could not be separated by chemical means, since their identical atomic numbers or nuclear electrical charges meant that they had the same chemical reactions in joining to form different compounds. They could be separated only by physical methods based on their slightly different mass weights. As uranium is extracted only with great difficulty, and in small amounts, from its ores, 99.28% of it is U-238, 0.71% of it is U-235, and only a trace is U-234. Thus, natural uranium has 140 times as much U-238 as U-235. It was soon discovered that U-235 was split by slow or very fast neutrons. But, when it split, it emitted very energetic neutrons traveling at high speeds. These fast neutrons would have to be slowed down to split any more U-235, but since U-238 gobbles up all neutrons which come by at intermediate speeds, chain reaction fission in uranium cannot occur in nature, where each atom of U-235 is surrounded by atoms of U-238 as well as by other neutron-absorbing impurities. From this it was clear that a chain reaction could be continued in either of two cases. One, if very pure natural uranium could be mixed with a substance called a moderator which would slow down neutrons without absorbing them, or two, if a mass of U-235 alone could be obtained so large that the fast neutrons emitted by fission would slow down to splitting speed before they escaped from the mass. The former reaction could probably be controlled, but the latter mass of U-235 would almost certainly explode spontaneously, since there are always a few slow neutrons floating around in space to start the chain reaction. Even in 1939 scientists guessed that ordinary water, heavy water made of hydrogen with a nucleus of a neutron and a proton instead of only one proton or carbon, would make good moderators for a controlled reaction. They also knew at least 4 ways in which, by physical methods, U-235 could be separated from U-238. At the very end of 1939, scientists had worked out what happened when U-238 gobbled up intermediate speed neutrons. It would change from 90 to U-238 to 90 to U-239, but almost at once the U-239, which is unstable, would shoot out a negative charge beta ray or electron from one of the 147 neutrons in its nucleus, turning that neutron into a proton, and leaving the weight at 239 while raising its positive charge's atomic number to 93. This would be a new element, one number beyond uranium, and therefore named Neptunium after the planet Neptune, one planet beyond Uranus as we move outward in the solar system. Theory seems to show that the new transuraniac element 93 Np239 would not be stable, but would soon, it turned out to be about 2 days, shoot out another electron from a neutron along with energy in the form of gamma rays. This would give a new transuraniac element number 94 with mass of 239. This second transuraniac element was called plutonium, with symbol 90 for Pu-239. At the very end of 1939, theory seems to indicate that this plutonium, like U-235, would be fissured by slow neutrons, if a sufficiently large lump of it could be made. Moreover, since it would be a different element, with 94 positive charges. It could be separated from the 92 U-238, in which it was created, by chemical methods usually much easier than the physical methods of separation required for isotopes of the same element. Theory reached this far by the spring of 1940. At that time, in the space of the months April to June, several things happened. 1. The Nazis overran Denmark and Norway, capturing Bohr in one country and the world's only heavy water factory in the other country. 2. News reached America that the Nazis had forbidden all further sales of Czechoslovakia's uranium ores and had taken over the greater part of Germany's major physical research laboratory, the Kaiser Wilhelm Institute in Berlin, for uranium research. 3. A blanket of secrecy was dropped throughout the world on scientific research on nuclear fission, and for the Nazis overran the Netherlands, Belgium, and France, capturing, among others, Joliet-Curie. At that time uranium was a largely worthless commodity, of which a few tons a year was used for coloring ceramics. It was produced only incidentally as a byproduct of efforts to produce other minerals such as cobalt or radium. Just before war began, Edgar St. Cyr, managing director of Union Minière of Katanga, Belgian-Congo, learned from Joliet-Curie his discovery of chain fission of uranium-23s. Accordingly, after the fall of France, St. Cyr ordered all available uranium ore, 1,250 tons of it, shipped to New York. This ore was 65% uranium oxide, compared to marketable North American ores of 0.2%, and the full-scale post-war exploitation of South African ores of 0.03%. For more than 2 years St. Cyr could find no one in the United States interested in his ores, which lay in a warehouse on Staten Island until the end of 1942. Just before the curtain of secrecy on atomic research fell in the spring of 1940, astounding information on the subject was published in Soviet Russia, but, like most Russian-language publications, was ignored in the outer world. In 1939 the Soviet Academy of Sciences set up, under the chairmanship of V.I. Vernadsky, director and founder 1922 of the Leningrad Radium Institute, an isotopes committee to work on the separation of uranium isotopes and the production of heavy water. The first cyclotron in Europe, an atom smasher of 4 million electron volts per meg which had been operational since 1937, went into full experimental use in April 1940, and, at the same time, the Academy of Sciences ordered immediate construction of a cyclotron of 1,1-meth, comparable to the world's largest, the 60-inch cyclotron at the University of California, operated by Ernest "Zero" Lawrence, the inventor of these machines. Nobel Prize, 1939. In this same fatal spring of 1940, the Conference on Isotope Separation in Moscow publicly discussed the problem of separation of U-235. Subsequently, Y. B. Karitan and Y. B. Seldovich published a paper on the problem of the critical mass for spontaneous explosion of this isotope, the kinetics of chain decomposition of uranium, in Journal Experimental Noise by Redishevskoy, X. 1940, 477. This was followed by publication of similar papers, some even in 1941, which might have shown clearly to anyone who wished to see that the Soviet Union was further developed than the United States at that time. No one, unfortunately, did wish to see. About the same time, Edwin A. Macmillan Nobel Prize, 1951, and Philip H. Abelson, using E. O. Lawrence's great cyclotron at Berkeley, California, had studied the results arising from neutron bombardment of uranium-238, and indicated the nature of 93 neptunium and the fissionable possibilities of 94 plutonium. Physical Review, June 15, 1940. Bohr, as well as Lewis A. Turner of Princeton, had already indicated some of the characteristics, including fissionability, of plutonium. The Soviet position in atomic research in 1940 is astonishing in view of the depredations inflicted on Soviet scientists by Stalin in the purges of 1937 to 1939. In June 1940, Soviet science in this subject was about on a level with that of the German scientists who remained in Nazi Germany, although both were far behind the refugee scientists who were still making their ways westward to the English-speaking world. The Soviet scientists were, apparently, interested in atomic research only for industrial power purposes, and were not much concerned with achieving atomic explosives. Accordingly, they concentrated on atomic piles of mixed uranium isotopes, rather than on uranium separation, and most of their work was suspended after the Nazi invasion in 1941. In a similar way, the remaining German scientists, although seeking the bomb, decided in February 1942 that large-scale separation of isotopes was too expensive to be practical, and spent the rest of the war years on the hopeless task of trying to devise an atomic pile which could be used as the bomb. The great German error was their failure to reach the conception of critical mass, the point which had been published in Russia in 1940. In the United States and Britain, the impact of the events of 1940 was much more intense among the refugee scientists than among the Americans. On the whole, the refugees had a higher level both of scientific training and of political awareness than the native scientists, and most of the outstanding American scientists had acquired their specialized knowledge in Europe, chiefly at Göttingen or elsewhere in Germany. As early as April 1939, a group of Hungarian refugees, led by Leo Szilard and including Eugen Wegner, Edward Teller, and John Juan Neumont, tried to establish a voluntary censorship of research information and to arouse the American government to the significance of the possible atom bomb. On March 17, 1939, Fermi visited the admiral in charge of the Technical Division of Navy Operations but could arouse no interest. In July, Szilard, driven once by Whitner and a second time by Teller, made 2 visits to Einstein and persuaded him to send a letter and memorandum to President Roosevelt through the banker Alexander Sachs. The President read the material on October 11, 1939, and the wheels of government began to move, but very slowly. Only on December 6, 1941, the day before Pearl Harbor, was the decision taken to make an all-out effort to unlock atomic energy. When the curtain of secrecy fell in June 1940, all the theory needed for the task was known by all capable physicists. What was not known was that their theories would work, and 2. how the immense resources needed for the task could be mobilized. As late as 1939, less than an ounce of uranium metal had ever been made in the United States. Now it was necessary to make tons of it in extremely refined form. To build an atomic pile for a controlled nuclear reaction, hundreds of tons of heavy water or of graphite refined to a degree hitherto unknown were also needed. This task, entrusted to the direction of Arthur H. Compton Nobel Prize, 1927, with Fermi doing the actual work, was set up at the University of Chicago. The pile of purified graphite with lumps of uranium all through it was built in a squash court under the west stands of Stagg Field, where football had been discontinued. The pile of graphite, shaped as a roughly flattened sphere about 24 feet in diameter, had 12,400 pounds of uranium in small scattered lumps distributed in a cube at its center. Neutron counters, thermometers, and other instruments kept track of the fission rate going on inside it. Before the top layers could be added, these indicators began to rise increasingly rapidly to danger levels. Therefore rods of cadmium steel were inserted through the graphite lattice. Cadmium, which absorbs large quantities of neutrons without being changed, could be used to hold back the fission process until the pile was finished. On December 2, 1942, before a team of scientists, these cadmium rods were slowly withdrawn to the point where a chain nuclear reaction took off. It could be damped down or speeded up to explosive level simply by pushing the rods in or pulling them out. This first sustained nuclear reactor was a great success, but it contributed little toward an atom bomb. Within it, at full operation, plutonium was made at a rate which would require 70,000 years to obtain enough for a bomb. This pile operated on purified natural uranium, in which the U-238 was 140 times the U-235. To separate U-235 from U-238 by physical methods, for techniques were attempted on parallel paths. 2 of these ceased to be significant after the end of 1943. The 2 survivors were gas diffusion and electromagnetic separation. In the latter, gaseous compounds of uranium were electrically charged so that they would move along a vacuum tube and pass through a powerful magnet which made them swerve. The heavier U-238 compounds would swerve less than the slightly lighter U-235 compounds, and the 2 could be separated. using the gigantic new cyclotron magnet at the University of California, which was 84 inches across. Ernesto Lawrence and Emilio Segre showed that it would require about 45,000 such units to separate a pound of U-235 a day. The electromagnetic separator plant called Y-12 as set up at Oak Ridge in 1943 covered 825 acres and was housed in 8 large buildings T/D of which were 543 feet by 312 feet. Several thousand magnets, most of which were 20 feet by 20 feet by 2 feet, consumed astronomical quantities of electricity in separating uranium isotopes into gigantic tanks. These tanks, weighing 14 tons each, were pulled out of line by as much as 3 inches by the magnetic attractions created, straining the pipes carrying uranium compound, and eventually they had to be fastened to the floor. Since copper for electrical connections was in such short supply, 14,000 tons of silver from the Treasury Reserve of American paper money was secretly taken from the Treasury vaults, although still carried publicly on the Treasury balance sheets, and made into wiring for the Y-12 plant. From this plant came much of the U-23s used in the Hiroshima A-bomb. The gaseous diffusion method, which had been carried fairly far by the British before America took it over, took advantage of the fact that atoms of lighter U-235 gas move more rapidly than the heavier U-238 and thus pass more rapidly through a porous barrier. If a mixture of the T/VO isotopes, in the only available gaseous form of the unstable and violently corrosive uranium hexafluoride, were pumped thus through 4,000 successive barriers, with billions of holes, each not over 4/10,000ths of an inch, the mixture after the last barrier would be largely the U-235 form of the compound Go% pure. By the end of April 1943, in 3 adjacent valleys near Oak Ridge, Tennessee, 3 plants were under construction for gaseous diffusion and electromagnetic separation of U-235 and for a large uranium pile to make plutonium out of U-238. By the end of the war, Oak Ridge, covering 70 square miles, had a population of 78,000 persons and was the 5th largest community in Tennessee. Because the plutonium plant was so dangerous, owing to its enormous generation of heat and radioactivity, a larger and more isolated plant was begun on a tract of 670 square miles near Hanford, Washington. A construction camp of 60,000 workers was set up there in April 1943. Construction of the first fission pile was begun in June, and it began to operate in January 1945. It is interesting to know that the 2 sites at Oak Ridge and Hanford were chosen for their proximity to the hydroelectric power plants of the Tennessee Valley Authority and Grand Coulee, which had been built by Roosevelt's New Deal. By the end of the war, nuclear production was using a large fraction of the total electricity produced in the United States, and would have been impossible without these great electrical generating constructions of the New Deal, which were still regarded with intense hatred by American conservatives. A third site, for research on the bomb itself and its final assembly, was built on a flat mesa near Los Alamos, New Mexico, 20 miles from Santa Fe. Robert Oppenheimer of the University of California, with the world's greatest assemblage of working scientists including almost a dozen Nobel laureates, planned and constructed the earliest bombs at that isolated spot. Until May 1, 1943, these complex projects were operated by committees and subcommittees of scientists, of which the chief chairmen were James B. Conant, Vannevar Bush, C.O. Lawrence, Harold Urey, and A.O. Compton. The actual construction work was delegated to the United States Army Corps of Engineers in charge of Leslie R. Groves, an expert on constructing buildings, whose chief achievement was the Pentagon building in Washington. From his graduation at West Point, Groves had held only desk jobs, had been a lieutenant for 17 years, and was still a major when war began. He was raised to brigadier general on his appointment as head of the Manhattan District, in charge of the physical administration of the atom bomb project in September. On May 1, 1943, he took over total charge of the whole project. An earnest, hard-working man, Groves had little imagination, no sense of humor, and not much familiarity with science or scientists whom he regarded as irresponsible long-hairs. Although he drove himself and his associates relentlessly, he greatly hampered the progress of the task by his fanatical obsession with secrecy. This obsession was based on his belief that the project involved fundamental scientific secrets. There were no such secrets. His efforts were quite in vain, as the only real secrets, the technological ones regarding isotope separation, critical mass, and trigger mechanisms of the bombs, were revealed to the Soviet Union almost as soon as they were achieved, by British scientists. The secrecy, thus, was secrecy for the American public rather than for the Germans or the Russians, neither of whom were actually seeking the information, since, like General Groves himself, they had little faith in the feasibility of the project. For security reasons, General Groves compartmentalized the work, and allowed only about a dozen persons to see the project as a whole. Consequently, the vast majority of those working on the project were not allowed to know what they were really doing or why, and this lack of perspective greatly delayed the solution of problems. The whole project of about 150,000 persons were segregated from their fellow citizens. All communications were cut off or censored, and the project was overrun with guards and security officials who did not hesitate to eavesdrop, read mail, monitor telephones, record conversations, and isolate individuals. These activities significantly delayed American achievement of the atom bomb without achieving their ostensible purpose, since there is no evidence either that the three enemy powers could have made the bomb or that Russia's making of the bomb was significantly delayed by General Groves's extreme degree of secrecy. General Groves's personal position was paradoxical. He took the assignment with disappointment and reluctance. had no real faith that the project would be successful until it actually was, carried secrecy to the nth degree, yet was convinced that the engineering problems were so colossal that the Soviet Union, even if it had the knowledge of how we did it, would be unable to repeat the achievement in less than 20 years, if ever. I myself heard General Groves make these statements in 1945. On the other hand, General Groves was a tireless and driving manager and an expert manipulator of the personal, political, and military arrangements which made the bomb possible. In the last 2 years of the project, July 1943-1945, it passed through crisis after crisis in a frenzied sequence which made it appear, every alternative month, that it would be a $2 billion fiasco. In January 1944, when the enormous gaseous diffusion plant at Oak Ridge was under full construction but without the diffusion barriers, since no effective ones could be made, it became necessary to junk the barriers on which tests had been made for almost 2 years and to turn to mass production of millions of square feet of a new barrier which had scarcely been tested. When this plant began to operate, section by section, at the end of the year, it worked so ineffectively that it seemed almost impossible that the concentration of U-235 could ever be raised over 15 or 20% without the construction of miles of additional barrier which would delay the bomb by months and use up fantastic quantities of uranium hexafluoride gas just to fill the chambers. Similarly, the electromagnetic separator plants suffered breakdown after breakdown, and operated at a level which made it seem impossible to raise the U-235 content over 50%. By April 1944, it seemed clear that 95% U-23s could not be obtained before 1946 even if the gas diffusion and electromagnetic plants were run in series instead of parallel, with the latter starting off with 20% U-235 from the former instead of both trying to process natural uranium from scratch. At that point, Oppenheimer discovered that Philip Abelson, who had originally discovered how to make uranium hexafluoride, had been working for the Navy, trying to make enriched U-235 to be used to propel a nuclear submarine. He was using thermal separation, one of the two methods. The other was centrifuge that the Manhattan District had rejected in 1942. Thermal separation was based on the fact that a liquid mixture in a container with a hot wall and an opposite cold wall will tend to separate. The heavier liquid will tend to accumulate near the cold wall, will cool, and sink, while the lighter liquid will tend to gather near the hot wall, get warmer, and rise. Abelson, who knew nothing of the work of the Manhattan District, or of the successful nuclear pile at Chicago, was working at the Philadelphia Navy Yard where he had 100 vertical, double concentric pipes, each 48 feet long, in which the inner pipe was heated by steam, the outer pipe was kept cool, and the ring-shaped space between the two was filled with a uranium liquid mixture whose two isotopes tended to separate from each other. From the top of these pipes he hoped to be able to draw 1/5 ounce a day of 5% U-235 by July 1, 1944. Gross grasped at this straw, and on June 27, 1944 signed contract for a thermal diffusion plant at Oak Ridge to be ready in 90 days. The new plant, which eventually cost over $15 million, was 522 feet long, 82 feet wide, and 75 feet high, and was to contain 21 exact copies of Abelson's Plant 2142 tubes in all. It would yield U-23s enriched to a few percentage points to be fed into the inadequate gas diffusion plant. It began to produce in March 1945. By placing the three separation methods in sequence and working night and day to improve the efficiency of all three, it began to look as if U-23 for one bomb might be available in the second half of 1945. These disappointments with U-23s naturally turned men's hopes to the plutonium being made at Hanford. When the first giant pile went critical there on September 27, 1944, it shut itself down after a day and then restarted itself again after another day. Frenzied study and consultation with the smaller piles at Oak Ridge and at Chicago finally revealed the unexpected production, within the pile, of the neutron-absorbing isotopes xenon-135, with a half-life of 9 hours. The pile started itself again when this decayed, and thus stopped draining neutrons from the uranium fission process. This problem was eventually solved by greatly increasing the uranium tubes in the pile. All through this worry, Los Alamos was having problems with the one-trigger mechanisms. Experiment and calculations eventually showed that the critical mass of U-235 was less than 1 pounds, about the size of a small grapefruit, if it were properly compressed and in spherical shape. To achieve this, two mechanisms were conceived, known as the gun and implosion. The gun was designed to create a critical mass high-shooting lump of U-235 at high velocity into a subcritical mass so that the combination would be over the critical mass. The resulting shape, however, was so unspherical that it was calculated that the whole amount of U-235 necessary for the gun trigger bomb would be almost twice the ideal critical mass. This increase from about 1 to about 21 pounds of U-235 per bomb would extend the date on which the bomb was ready by weeks, since the output of U-235 was so small. The second trigger, called implosion, planned to make a hollow sphere of U-235 or plutonium, which was critical in total amount but kept subcritical by the hole in the center. This metallic sphere would be crushed together into the space in its center to make the critical mass there by the explosion of 20 or more crescent-shaped pieces of TNT which surrounded the sphere. The difficulty was that all the surrounding TNT had to explode at the same instant in order to ramp the nuclear material together at the center. any lamp would simply bulge the nuclear material erratically and prevent the achievement of critical mass. All the ordnance experts, including Captain Parsons, of the United States Navy, in charge of this part of the work at Los Alamos, were convinced that such accurate timing of TNT explosion, with 24 pieces exploded within a millionth of a second, would be impossible. This brought up another crisis because Glenn Seaborg Nobel Prize 1951 and Seth Gray predicted and then demonstrated that the plutonium-238 which they were seeking from the Hanford pile spontaneously changed itself, at a slow rate, into its isotope plutonium-240. Since Pu-240 was a spontaneous fissioner, this impurity would prematurely explode the target mass of plutonium in the gun-type trigger, since the inefficiency of the gun mechanism made it necessary to have the target mass so large perfectly safe with U-235, but suicide with Pu-238 if there was Pu-240 in it also. The plutonium, therefore, had to be used with an implosion trigger, and, if that could not be devised, the $400 million cost of the Hanford plant had been practically thrown away. Fortunately, George Kistiakowsky, chemistry professor from Harvard and a great authority on explosives, came to Los Alamos, and by the spring of 1945 had worked out an ignition by which all the TNT would explode within a few millionths of a second. This saved the plutonium scheme, but it was clear that this material would hardly be available in a bomb amount until late summer of 1945 and that there would not be enough to test the implosion trigger on it, if it were to be used in the war. By July 1945, everyone concerned with the bomb was working around the clock, and a few had begun to fear that the war would be over before the bomb would be ready. On the other hand, a group of the scientists, led by Szilard who had instigated the project, were beginning to agitate that the bomb should not be used against Japan. Their motives have been questioned since, but were both simple and honorable. They had pressed for the atom bomb in 1939 because they feared that Germany was working on one and might get it first. Once the defeat of Germany ended that danger, many scientists regarded continued work on the bomb as immoral and no longer defensive since there was no chance of Japan's developing one. No one in July 1945 realized that all the significant information about making the bomb, notably the relative merits of different kinds of uranium, methods of plutonium separation, and the two kinds of trigger mechanisms, had been sent on to the Soviet Union, chiefly from Klaus Fuchs and David Greenglass by way of Harry Gold and Anatoly Yakovlev in June 1945. Even today American security agents are trying to keep secret these facts which have been fully explained in easily available technical publications. For many years after 1945 the American people were kept in a state of alarm by stories of networks of atomic spy rings, made up of Communist Party members or sympathizers. who were prowling the country to obtain by espionage what the Soviet Union was unable to achieve by its own efforts in scientific research and industrial development. When we speak of atomic secrets and spying, we must distinguish three quite different types of information. 1. Scientific principles. 2. Questions of general production tactics such as which methods are workable or unworkable, and 3. Detailed information of engineering construction. No secrets of Group I existed, and secrets of Group 3 would usually have required elaborate blueprints and formulas which could not be past high spying methods of communication. There remains information of Group 2, which could be extremely helpful in saving wasted time and effort. In most cases, information of this type would have little meaning to anyone without a minimum of scientific training. This kind of information, so far as present information allows the judgment, would seem to have been passed to the Russians from two English scientists, Alan Nunn and Claus Fuchs, and an American Army enlisted man, David Greenglass, in the period to September 1945. Nunn may had little directly to do with the A-43OMB, but he had worked on the heavy water nuclear pile in Canada and had visited the graphite pile in Chicago several times. He gave Soviet agents Lieutenant Angelov and Colonel Zabutin, in Canada, considerable information about atomic piles, as well as the daily output of U-235 and plutonium at Oak Ridge 400 and 800 grams, respectively, and handed over a trace of the uranium isotope U-233. The information from Fuchs, which was much more valuable, culminated about the same period, June 1945, and gave information on gaseous diffusion, the two trigger devices, and the fact that work had been done without much success toward a fusion H-bomb. Greenglass, at the same time, gave the same Russian contact, Harry Gold, a rough sketch of part of the implosion trigger for the A-bomb. There may have been other spying episodes of which we are not now aware, but the information passed to the Russians of which we are now aware probably did not contribute much significant aid to their achievement of the A-bomb. The H-bomb will be considered later. Statements frequently made that the Russians could not have made the A-bomb without information obtained from espionage, or statements that such information speeded up their acquisition of the bomb by years or even by 18 months are most unlikely, although here again we cannot be sure. They must have been saved from trying some unremunerative lines of endeavor, but the real problems in making the bomb were engineering and fiscal problems, which Russia could overcome on a crash basis, once it was known that we had such a bomb. This knowledge was given to the world by the destruction of Hiroshima. The decision to use the bomb against Japan marks one of the critical turning points in the history of our times. The scientists who were consulted had no information on the status of the war itself, had no idea how close to the end Japan already was, and had no experience to make judgments on this matter. the politicians and military men had no real conception of the nature of the new weapon or of the drastic revolution it offered to human life. To them it was simply a bigger bomb, even a much bigger bomb, and, by that fact alone, they welcomed it. Some people, like General Groves, wanted it to be used to justify the $2 billion they had spent. A large group sided with him because the Democratic leaders in the Congress had authorized these expenditures outside proper congressional procedures and had cooperated in keeping them from almost all members of both houses by concealing them under misleading appropriation headings. Majority Leader John W. McCormick, later Speaker, once told me, half-joking, that if the bomb had not worked he expected to face penal charges. Some Republicans, notably Congressman Albert J. Engel of Michigan, had already shown signs of a desire to use congressional investigations and newspaper publicity to raise questions about misuse of public funds. During one War Department discussion of this problem, a skilled engineer, Jack Madigan, said, "JJ, the project succeeds, there won't be any investigation. JJ, it doesn't, they won't investigate anything else." Moreover, some Air Force officers were eager to protect the relative position of their service in the post-war demobilization and drastic reduction of financial appropriations by using a successful A-bomb drop as an argument that Japan had been defeated by air power rather than by naval or ground forces. After it was all over, Director of Military Intelligence for the Pacific Theater of War, Alfred McCormick, who was probably in as good position as anyone for judging the situation, felt that the Japanese surrender could have been obtained in a few weeks by blockade alone. The Japanese had no longer enough food in stock, and their fuel reserves were practically exhausted. We had begun a secret process of mining all their harbors, which was steadily isolating them from the rest of the world. If we had brought this operation to its logical conclusion, the destruction of Japan's cities with incendiary and other bombs would have been quite unnecessary. But General Northstadt declared at Washington that this blockading action was a cowardly proceeding unworthy of the Air Force. It was therefore discontinued. The degree to which it has since been distorted for partisan purposes may be seen from the contradictory charges that the efforts to get a bomb slowed down after the defeat of Germany and the opposite charge that they speeded up in that period. The former charge, aimed at the scientists, especially the refugees at Chicago who had given America the bomb by providing the original impetus toward it, was that these scientists, led by Szilard, were anti-Nazi, pro-Soviet, and un-American, and worked desperately for the bomb so long as Hitler was a threat. But on his demise opposed all further work for fear it would make the United States too strong against the Soviet Union. The opposite charged bombs that the Manhattan District worked with increasing frenzy after Germany's defeat, because General Groves was anti-Soviet. A variant of this last charge is that Groves was a racist and was willing to use the bomb on non-whites like the Japanese but unwilling to use it against the Germans. It is true that Groves in his report of April 23, 1945, which was presented to President Truman by Secretary Stimson 2 days later, said that Japan had always been the target. The word "always" here probably goes back only to the date on which it was realized that the bomb would be so heavy that it could not be handled by any American plane in the European theater and, if used there, would have to be dropped from a British Lancaster. While in the Pacific the B-29 could handle it. The original decision to make the bomb had been a correct one based on fear that Germany would get it first. On this basis the project might have been stopped as soon as it bombs clear that Germany was defeated without it. By that time other forces had come into the situation, forces too powerful to stop the project. It is equally clear that the defeat of Japan did not require the A-bomb, just as it did not require Russian entry into the war or an American invasion of the Japanese home islands. But, again, other factors involving interests and non-rational considerations were too powerful. However, if the United States had not finished the bomb project or had not used it, it seems most unlikely that the Soviet Union would have made its post-war efforts to get the bomb. There are several reasons for this. 1. The bomb's true significance was even more remote from Soviet political and military leaders than from our own, and would have been too remote to make the effort to get it worthwhile if the bomb had never been demonstrated. 2. Soviet strategy had no interest in strategic bombing, and their final decision to make the bomb, based on our possession of it, involved changes in strategic ideas, and the effort, almost from scratch, to obtain a strategic bombing plane, the Tu-4, able to carry it, and 3. The strain on Soviet economic resources from making the bomb was very large, in view of the Russian war damage. Without the knowledge of the actual bomb which the Russian leaders obtained from our demonstration of its power, they would almost certainly not have made the effort to get the bomb if we had not used it on Japan. Russia was also working on the bomb. Russia was well aware of German progress in bomb development at the time. On the other hand, if we had not used the bomb on Japan, we would have been quite incapable of preventing the Soviet ground forces from expanding wherever they were ordered in Eurasia in 1946 and later. We do not know where they might have been ordered because we do not know if the Kremlin is insatiable for conquest, as some experts claim, or is only seeking buffer security zones, as other experts believe. But it is clear that Soviet orders to advance were prevented by American possession of the A-bomb after 1945. It seemed clear that ultimately Soviet forces would have taken all of Germany, much of the Balkans, probably Manchuria, and possibly other fringe areas across Central Asia, including Iran. Such an advance of Soviet power to the Rhine, the Adriatic, and the Aegean would have been totally unacceptable to the United States. But, without the atom bomb, we could hardly have stopped it. Moreover, such an advance would have led to communist or communist-dominated coalition governments in Italy and France. If the Soviet forces had advanced to the Persian Gulf across Iran, this might have led to such communist-elected governments in India and much of Africa. From these considerations, it seems likely that American suspension of the atomic project after the defeat of Germany or failure to use the bomb against Japan would have led eventually to American possession of the bomb in an otherwise intolerable position of inferiority to Russia, or even to war in order to avoid such a position, but with little hope from war, to avoid such inferiority. This would have occurred even if we assume the more optimistic of two assumptions about Russia: one, that they would not themselves proceed to make the bomb, and two, that they are not themselves insatiably expansionist. On the whole, then, it seems that the stalemate of mutual nuclear terror without war in which the world now exists is preferable to what might have occurred if the United States had made the decision either to suspend the atomic project after the defeat of Germany or to refuse to use it on Japan. Any other possible decisions, such as an open demonstration of its power before an international audience in order to obtain an international organization able to control the new power, would probably have led to one of the two outcomes already described. But it must be clearly recognized that the particular stalemate of nuclear terror in which the world now lives derives directly from the two decisions made in 1945 to continue the project after the defeat of Germany and to use the bomb on Japan. This nuclear stalemate, in turn, leads to pervasive consequences in all aspects of the world in the 20th century. It gives rise to a frenzied race between the two superpowers to outstrip each other in the application of science and rationality to life, beginning with weapons. This effort provides such expensive equipment and requires such skill from the operators of this equipment that it makes obsolete the army of temporarily drafted citizen soldiers of the 19th century and of the armed hordes of World War I and even of World War II, and requires the use of highly trained, professional, mercenary fighting men. The growth of the army of specialists, foretold by General de Gaulle in 1934 and foreseen by others, destroys one of the three basic foundations of political democracy. These three bases are: I, that men are relatively equal in factual power; 2, that men have relatively equal access to the information needed to make the government's decisions; and 3, that men have a psychological readiness to accept majority rule in return for those civil rights which will allow any minority to work to build itself up to become a majority. Just as weapons development has destroyed the first of these bases, so secrecy, security considerations, and the growing complexity of the issues have served to undermine the second of these. The third, which was always the weakest of the three, is still in the stage of relative vitality and relative acceptability that it had in the 19th century, but is in much greater danger from the threat of outside forces, notably the changes in the other two bases, plus the greater danger today from external war or from domestic economic breakdown. One great danger in regard to the second of these basic foundations, availability of information necessary for decision-making, is the impact upon it of the expansion of rationalization. While this has led to automatic and mechanical storage and retrieval of information, it has also led to efforts to establish automatic electronic decision-making on the basis of the growing volume and complexity of such information. This renunciation of the basic feature of being human, judgment and decision-making, is very dangerous and is a renunciation of the very faculty which gave man his success in the evolutionary struggle with other living creatures. If this whole process is now to be abandoned in favor of some other, unconscious and mechanical, method of decision-making, in which the individual's flexibility and awareness are to be subordinated to a rigid group process, then man must yield to those forms of life, such as the social insects, which have already carried this method to a high degree of perfection. This whole process has been made the central focus of the recent novel, Fail-Safe, by Eugene Burdick and Harvey Wheeler. The reduction of men to automatons in a complicated nexus of expensive machines is well shown in that book. To its picture must be added 2 points. One, it does not require a blown condenser, as in the book, to unleash the full dangers of the situation. It is a situation which is dangerous in itself even if it functions perfectly. And 2, the avoidance of the ultimate total catastrophe in the book, because a few men, that and near the top, were able to resume the human functions of decision, self-sacrifice, love of their fellow men, and hope for the future, should not conceal the fact that the whole world in that story came within minutes of handing its resources over to the insects. Regardless of the outcome of the situation, it is increasingly clear that, in the 20th century, the expert will replace the democratic voter in control of the political system. This is because planning will inevitably replace laissez-faire in the relationships between the two systems. This planning may not be single or unified, but it will be planning, in which the main framework and operational forces of the system will be established and limited by the experts on the governmental side. Then the experts within the big units on the economic side will do their planning within these established limitations. Hopefully, the elements of choice and freedom may survive for the ordinary individual in that he may be free to make a choice between 2 opposing political groups even if these groups have little policy choice within the parameters of policy established by the experts, and he may have the choice to switch his economic support from one large unit to another. But, in general, his freedom and choice will be controlled within very narrow alternatives by the fact that he will be numbered from birth and followed, as a number, through his educational training, his required military or other public service, his tax contributions, his health and medical requirements, and his final retirement and death benefits. Eventually, in 2 or 3 generations, as the ordinary individual who is not an expert or a skilled professional soldier or a prominent industrial executive becomes of less personal concern to the government, his contacts with the government will become less direct and will take place increasingly through intermediaries. Some movement in this direction may be seen already in those cases where taxpayers whose incomes are entirely from wages or salaries find that their whole tax is already paid by their employer, or in the decreasing need for the military draftee to be called to serve by a letter from the President. The development of such a situation, a kind of neo-feudalism, in which the relationships of ordinary people to government cease to be direct and are increasingly through intermediaries or private rather than public authorities, has already arrived. One consequence of the nuclear rivalry has been the almost total destruction of international law and the international community as they existed from the middle of the 17th century to the end of the 19th. That old international law was based on a number of sharp rational distinctions which no longer exist. These include the distinction between war and peace, the rights of neutrals, the distinction between combatants and non-combatants, the nature of the state, and the distinction between public and private authority. These are now either destroyed or in great confusion. We have already seen the obliteration of the distinctions between combatants and non-combatants and between neutrals and belligerents brought on by British actions in World War I. These began with the blockade of neutrals, like the Netherlands, and the use of floating mines in navigational waters. The Germans retaliated with acts against Belgian civilians and with indiscriminate submarine warfare. These kinds of actions continued in World War I with the British night bombing effort aimed at destroying civilian morale by the destruction of workers' housing, Lord Charles's favorite tactic, and the American fire raids against Tokyo. It is generally stated in American accounts of the use of the first atom bomb that target planning was based on selection of military targets, and it is not generally known even today that the official orders from cabinet level on this matter specifically said military objectives surrounded by workers' housing. The post-war balance of terror reached its peak of total disregard both of non-combatants and of neutrals in the policies of John Foster Dulles. Who combined sanctimonious religion with massive retaliation wherever and whenever we judge fit to the complete destruction of any non-combatant or neutral status. Most other aspects of traditional international law have also been destroyed. The Cold War has left little to the old distinction between war and peace, in which sealed wars had to be formally declared and formally concluded. Hitler's attacks without warning, the Korean War, which was not a war in international law or in American constitutional law since it was not declared by Congress, and the fact that no peace treaty has been signed with Germany to end World War I, while we are already engaged in all kinds of undeclared warlike activities against the Soviet Union, have combined to wipe out many of the distinctions between war and peace which were so painfully established in the 500 years before Grotius died in 1645. Most of these losses obvious, there are others, equally significant, not yet widely recognized. The growth of international law in the late medieval and Renaissance periods not only sought to make the distinctions we have indicated, As a reaction against feudal disorder, it also sought to make a sharp distinction between public and private authority in order to get rid of the feudal doctrine of dominia and to set up sharp criteria of public authority involving the new doctrine of sovereignty. One of the chief criteria of such sovereignty was ability to maintain the peace and to enforce both law and order over a definite territory. One of its greatest achievements was the elimination of arbitrary non-sovereign private powers such as robber barons on land or piracy on the sea. Under this conception, the ability to maintain law and order became the chief evidence of sovereignty, and the possession of sovereignty became the sole mark of public authority and the existence of a state. All this has now been destroyed. The Stimson Doctrine of 1931. In the American refusal to recognize Red China, shifted recognition from the objective criterion of ability to maintain order to the subjective criterion of approval of the form of government or liking of a government's domestic behavior. The destruction of international law, like the destruction of international order, has gone much further than this. As long as the chief criterion for a state's sovereignty, and hence of recognition, was ability to maintain order, states in international law were regarded as equal. This concept is still recognized in theory in such organizations as the Assembly of the United Nations. But the achievement of nuclear weapons, by creating two superpowers in a Cold War, destroyed the fact of the equality of states. This had the obvious result of creating powers on two levels, ordinary and super, but it had the less obvious, and more significant, consequence of permitting the existence of states of lower levels of power, far below the level of ordinary powers. This arose because the nuclear stalemate of the two superpowers created an umbrella of fear of precipitating nuclear war which falsified their abilities to act at all. As a result, all kinds of groups and individuals could do all kinds of actions to destroy law and order without suffering the consequences of forcible retaliation by ordinary powers or by the superpowers, and could become recognized as states when they were still totally lacking in the traditional attributes of statehood. For example, the Leopoldsville Group were recognized as the real government of the whole Congo in spite of the fact that they were incapable of maintaining law and order over the area or even in Leopoldsville itself. In a similar way, a gang of rebels in Yemen in 1962 were instantly recognized before they gave any evidence whatever of ability to maintain control or of readiness to assume the existing international obligations of the Yemen state, and before it was established that their claims to have killed the king were true. In Togo in the following year, a band of disgruntled soldiers killed the president, Sylvanus Olympio, and replaced him with a recalled political exile. Under the umbrella of nuclear stalemate, the boundaries of old states are shattered by guerrillas in conflict, supported by outsiders. Outside governments subsidize murders or revolts, as the Russians did in Iraq in July 1958, or as Nasser of Egypt did in Jordan, Syria, Yemen, and elsewhere in the whole period after 1953, and as the American CIA did in several places, successfully in Iran in August 1953, and in Guatemala in May 1954, or very unsuccessfully, as in the Cuban invasion of April 1961. Under the Cold War umbrella, small groups or areas can obtain recognition as states without any need to demonstrate the traditional characteristics of statehood, namely, the ability to maintain their frontiers against their neighbors by force and the ability to maintain order within these frontiers. They can do this either by securing the intervention, usually secret, of some outside power, or even by preventing the intervention of a recognized power fearful of precipitating nuclear or lesser conflict. In this way, areas with a few states such as Southeast Asia were shattered into many. States went out of existence or appeared as Syria did in 1958 and 1961, and so-called new states came into existence by scores without reference to any traditional realities of political power or to the established procedures of international law. The number of separate states registered as members in the United Nations rose steadily from 51 in 1945 to 82 in 1958 to 104 in 1961, and continued to rise. The difference in power between the strongest and the weakest became astronomical, and the whole mechanism of international relations, outside the organization as well as within it, became more and more remote from power considerations or even from reality, and became enmeshed in subjective considerations of symbols, prestige, personal pride, and petty spites. By 1963, single tribes in Africa were looking toward recognition of statehood through membership in the UN, even when they lacked the financial resources to support a delegation at UN headquarters in New York City or in the capitals of any major country, and were, indeed, incapable of controlling police forces to maintain order in their own tribal areas. In this way, the existence of nuclear stalemate within the Cold War carried on the total destruction of traditional international law and the gradual loss of meaning of the established concepts of state and public authority, and opened the door to a feudalization of authority somewhat similar to that which the founders of the modern state system and of international law had sought to overcome in the period from the 12th century to the 17th.